Today begins projectile motion. Okay. So a couple of definitions here. So projectile motion involves a couple things. Constant free fall acceleration. We're going to see that even though velocity of an object through the air has two components, only the vertical component of velocity is going to be affected by gravity because it's the vertical component that is in the same axis as the acceleration of gravity. There is no affect in the x-axis. So the horizontal component of velocity will remain unchanged because we are, one, assuming that there's no real air resistance to provide an acceleration, aka a force against the velocity in the x direction. And two, gravity just doesn't appear in the x direction. It's not horizontal, it's vertical. So those are two things that we're going to keep in mind. Two additional things. So it involves constant free fall acceleration, and we know that that is equal to 9.81 meters per second squared. And as I mentioned before, we're going to assume no real air resistance. Air resistance for the moment will be negligible. Soon we will consider air resistance, and then things get interesting. They get more realistic, more fun. All right. With these assumptions, the path of the projectile is parabolic. It's an upside down parabola. The function is negative ax squared plus bx plus c. But we're going to translate that into physics. Kinematic equation that involves y equals vit minus 1/2 gt squared is the physical analog of that upside down parabola, where, as you can tell, negative ax squared is negative 1/2 gt squared plus vit plus y initial if there is an initial vertical position. So it's a parabolic path like this, which I mentioned is the application of that quadratic equation, which is, I'm going to say 4.9 because that's 1/2 g. 4.9 t squared plus vit plus y initial. That's c, that's b, that's a. Upside down parabola. Math, physics. We have seen this. Okay. Or, better yet, and most accurately, this would be delta y in order to make the full form of the quadratic, correct? Equals 0. Equals 0. Are we tracking that? Does everybody see what I mean there? Thought I saw. Okay. Let me write that a little clearer. X squared plus bx plus c equals 0. Quadratic equation, solve for x, negative b plus or minus, blah, 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 blah. Well, when we have that in terms of physics, we can solve for t using the same logic. Negative 4.9 t squared, where t is in the x-axis, plus v, technically, this will become, we'll see in a moment, vy initial t plus delta y equals 0. Math to physics analog. upside down parabola. Everything fits, math to physics. The physical pathway from the mathematical relationship of negative ax squared plus bx plus c, da, 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 da. And of course, we have the other equations. Parabolic. Just wanted to get that background for you to help you appreciate why, how path is parabolic. So now let us put some meat on the bones. We have this upside down parabola. Maximum height, momentarily something is 0. Not y versus t or x versus t, y versus x. Simultaneous pathways. A projectile has an angle theta. It will be projected at some large velocity along the tangent here. And we know that that's going to be large by the slope. Then it gets smaller at the top, something gets smaller, and then it gets larger negative. We have seen this graph. We've gone motion in a straight line, extending your concepts. We've seen the little funky curves. And so we should have a full appreciation of how this works. This is our velocity at an angle. We have just established in the last 3 days that velocity vectors, like velocity at angles, have 2 parts in our general perspective of the XY plane. So this is V now, okay, V sub x, Vx initial, if this is I. And then this would be Vy initial. Hence, the slight allusion to that kinematics equation, delta y is equal to VIT minus 1/2 GT squared, but it's not just VI, it's Vy initial. I'll be rewriting these equations because there is a component of velocity in the vertical direction that is affected by gravity. Hope you guys are tracking that. This is point A, the beginning. Shoots off, cannon shoots up.
Sort of, I need to try harder. Hi, Mr. Kelly, welcome back.
Thank you. I have a very unstable connection, apparently, this morning. All right, let's get back to it. Was everybody following up to this part that I think I ended here?
Yes.
So, right, so that's my initial picture, angle theta. And then as we see, as this particle travels through time, this velocity vector gets smaller. But the x component, of course, not to scale and all that stuff, the x component doesn't change. The y component does. So there's different ways of depicting that. Okay, so we have, I guess I'll just keep on saying VI there. Vx initial, y initial. Then say that is point B and point C. The only component, or there is a component that exists, that is just the x component. The y component for a moment is equal to 0. It's vanished. Because at the maximum height, temporarily, the y component of the speed vanishes. And the only component that remains is the x component. All right, so that's like a part point C. So this is kind of like mirror image kind of thing. And then, right, because gravity is slowed this down to 9.81, and then we reach the maximum height, it's 0, then we continue on. So before I get to point D though, at C, the maximum height I'll just say Vy final is equal to 0. Only for an instant. But the x component remains, or else if things are thrown up into the air, they reach their maximum height, they fall back down. However, they continue going on under the, mute that mic, please. Under the influence of the x component of velocity. So it keeps going forward, even though momentarily at the maximum height. And that's something else you want to keep in mind too for problems that say, okay, at the maximum height, how much time does it take to get up there? Well, you already know at the maximum height for an instant of the velocity of Vy final is going to be equal to 0. So you can put it into an equation, Vy final squared equals Vy initial squared minus 2gd to get, say, the distance to the maximum height, and then you can figure out how much time it takes to get there very easily because you know that concept. And then point D here, let's say it continues on. We have now become the mirror image of this, basically. And then, so D and E, so we basically have this effect. Oop. So the projectile at part E will hit the ground with a y component of speed and an x component. This is Vy final, Vx final, V final. So everything over here is the final case or the second case. Will. Not exact, but it's for illustration purposes. We have a mirror image here. And this mirror image only works if the initial position is equal to the final position. If it starts and stops at the same point, everything is mirrored. The time it takes to go up to the maximum height is exactly equal to the time it takes to come down. The velocity initial on the left-hand side of the mirror is equal to the velocity on the right-hand side. The components are going to be equal. Vy initial in one phase, in phase B as in boy, will be the same thing as D, as in dog here. And so on, they're exact mirrors. In biology, this is called bilateral symmetry. All human beings have bilateral symmetry. In nature, bilateral. It's like a line that cuts through and you have two eyes and so on, right? So everything fits as a mirror. But this mirror image effect right, only works if y initial is equal to y final. You're going to have asymmetry. Sometimes your y initial will be here and your y final will be down here somewhere. The ground will be below. This is going to you'll be at the top of a building. So you have to play around with it a tiny bit. It's not going to be that complicated, but you don't have the nice little symmetry. You don't have the mirror image. But anytime you have the initial vertical position is equal to the final vertical position, mirror. And here are some conditions for that mirror image, okay? I mentioned them earlier. The up time, the time it takes to get to the maximum height, is exactly equal to down time. Time period is the same for both directions. That should make common sense. It takes you the same amount of time to go up as it is to go forward. You don't get to a y component or a y position, faster than the x position. doesn't make sense. And so Vy initial is going to be the negative of Vy final. Magnitude is the same, but the direction is different because over here it's coming down, over here it's going up positive, and then that's negative. So technically, you don't have to do that, but you know orientation-wise that that's going to be negative. And negative here, and x never changes. That's no matter what. Symmetry, mirror image symmetry, asymmetry. Vx initial equals Vx final equals Vx equals. That does not change because we are assuming no air resistance. Pardon me for my writing there. And no gravity in x direction. You don't fall side to side, you fall down. So x doesn't change. These are just things that you want to have in your toolkit when you're going to solve problems in projectile motion. This is constant. You may or may not need to use this a lot, but it's something to keep in mind. But this uptime, downtime thing comes up a lot. So just keep that in mind. And I forgot to say, no matter what, if you're in a symmetric or asymmetric situation, Ey final at max height will always be 0 because at that point, gravity has slowed the velocity in the vertical direction to 0 speed at that point. And for that moment, Vy final is 0. And then it changes direction. We have seen that before graphically. It should be all too familiar. Large rate of speed, Vy initial, momentarily 0 and continues in the negative direction. That is exactly the velocity graph of this curve. We have negative ax squared. We now have a negative 2ax. Then we get negative 2a, or just constant for acceleration. And we know that acceleration is gravity. So here is where Vy final is momentarily 0, but it continues. Negative slope, dt, on and on. Symmetry of position, just like we have symmetry here. Everything fits, everything is beautiful, everything's harmonious, right? And we have, well, acceleration due to gravity, like there. This is negative 9.81, on and on, no matter what. So gravity slows the object down at 9.81 meters per second, 0, non-differentiable, but gravity is still there. That's another, but that's, really the reason why it changes position. They have a horizontal speed, but gravity keeps on changing the vertical component from positive to 0, 0 to large negative, or positive to 0 to negative. So yeah, so we're just now putting out all those pieces together. Any questions on that bit? Well, anything you need to see? All right, so if there's nothing there, let's continue. Let's look at the components of this velocity here. I guess I can continue in red here. So let's look at the initial X and Y components. Now that we've had some vectors and all that stuff, it has a little appreciation for this breakup of the components. So again, my velocity hypotenuse initial, on the left-hand side, and I have my Vx initial. These are all vectors as well, as you know. I and arrow. We know that cosine of theta is adjacent over hypotenuse. Sine is opposite over hypotenuse. If we wanted to find the value for Vx initial or Vx period, you just multiply, the Vx's and stuff, right? That'll be Vi cosine theta. And likewise, Vi initial is Vi sine theta. You know your angle, you know your initial velocity, you can find out what Vy is, or probably tell you, it just depends on the situation. Hopefully you're tracking that okay. It's all the same junk. Got you upside down parabola. You've seen the graphs. BT, AT, right triangles. Now we're just not saying this used to be C. Oh boy. I just saw my pen battery low, but I'm gonna throw it in there for a minute and just talk about it. So we used to see C here. Let's see if that affects anything. Okay, C and you can't see me pointing. A, B, C, or C for hypotenuse, but now we're looking at it from real physics, where C is VI, A is VXI, B is VY initial, but the logic is the same. Okay. Please mute your background, please. All right, so like I said before, when analyzing projectile motion, please stop me if you have any questions. This is always good to do that in the beginning. Concepts. When analyzing projectile motion, it's the superposition of two motions, a motion in X direction, Y direction. I've already said this, but I'm just writing it out. There will be constant velocity along the X axis, and then two constant acceleration along or the y-axis. Okay.
Mr. Kelly, what do you mean by superposition?
And it's basically the joining. It's all right. Simply put, it's just like you're moving in two directions.
Okay.
Yeah. So two directions at once. Let's see how we can group this together here. Okay. Let's see. Next thing I want to talk about is this thing with horizontal range and maximum height. The example in your book, and I'm just going straight from there, they're depicting a situation where you can get the equation for maximum height in terms of the trigonometric functions, sines and cosines. So a couple of equations that they're going to be taking a look at is the version of VF equals VI minus GT, but we know that there's two directions for velocity, so this is really going to be VFY equals VYI minus GT. The first thing they did is to get an equation for time. How much time does it take to get to the maximum height? And then you substitute that expression into the delta y equation, VIT minus half GT squared, in order to get a new version of the same thing in terms of sines, in terms of the trig functions. And that's just like a useful tool. I mean, you can rearrange the same things instead of just having VYIs and stuff all over the place. You just have it in your easier sines and cosines where appropriate, right? So the first thing that we wish to do is this curve like so, and this is our maximum height that we're considering. The velocity at A, or the maximum height, we already established that's going to be 0. Vi is our initial speed. Theta I, or just theta. We're going to assume that theta is going to be the same thing all the way through. We're not, going to have any sort of wind resistance to change theta or mess around with theta. So it's all the way through. And instead of saying delta x, the common term is our range. But you can say delta x, it's the same thing. R is equal to Vxi cosine t, or x equals Vi cosine theta t. So here's A, and here is B. So the first thing that they, just find time to reach maximum height. And then get new expression for max height. So we just have to walk ourselves through each part of this journey. What's going on at the maximum height? We know that the final speed for that moment is equal to 0. We know that there's gravity, and we had an initial speed right here. But we're talking about height, so we're talking about everything in the y-axis. So our final expression will not have anything to do with VI. It will have everything to do with VYI, or the velocity in the vertical axis. Okay, so taking that equation again, and it's GT for one moment. We know that this is 0 at point A. GT at max height A. And they rearrange it in terms of the sines. So VYI is going to be VI sine theta minus GT from before, where we just derived for VY initial. And then this T is going to be your uptime. How much time does it take to get up to the max height? This will then be negative VI sine theta over negative G. The negatives cancel out. So you could say uptime is VYI divided by G, but what if you don't know, what VI is, or you can find out, you can find it obviously from this expression VI sine theta. So it's just in terms of the signs, in terms of theta, what is T? So it'd be VI sine theta over G. Okay, so next thing is to figure out your maximum height, which is your y final minus y initial. Y initial is equal to 0, so it's basically just y final. All these mean the same thing. Okay, so right, this is going to be equal to dyit minus 1/2 gt squared. So we go everywhere in this equation and replace t's with this expression. And that's what they did, just have a new expression for height in terms of signs. So, and VYI as well. So H equals VI sine theta. The T was VI sine theta over G minus 1/2. I'm just going to say 4.9. Oh boy. VI sine theta over G squared. Then you just, you can simplify that. VI squared sine squared theta over G. For this guy, and then of course the simplification. So then 4.9 VI squared sine squared theta over G squared. Okay, so that this is this expression, and this is this guy here. The common denominator, all that stuff, but I'm just gonna save all that middleman math. You can do that and just write out the final expression. That comes out to be VI squared sine squared theta over 2G. So basically, this is convenient because if you want to find, all things being equal, if you want to find the maximum height and you have a symmetric problem, you can just use this expression. I don't advocate, oh, this is the expression that you should use here. I never do that. I don't like that. But whatever fits, every problem is going to be different. You get caught up in finding out what equations to use versus what's the best. There's issues, you get stuck in all that. So this is the, maximum height equation in terms of signs. And there's an analog to it in horizontal range. For maximum horizontal distance or range, the total time will be equal to the uptime plus the downtime, or total is twice uptime. That's just saying the same thing. It's just redundant. Okay, everybody see that? So we go back. The time that takes to go up here in a symmetric problem is the same time to come back down. So this is double. If it's 2 seconds to go up, 2 seconds to come down, total time is 4 seconds.
So that's the range.
Go ahead.
So what's the range again?
Well, I wasn't talking about the range per se. I was saying that the time it takes to travel the range is twice the uptime. And now I'm going to talk about the equation for range. Okay, range R, or delta X, the horizontal distance, is Vxi or Vxf, or just Vx, really, right? Cosine theta times t. Now this t is total because it takes me a total amount of time to cover all that distance. And so I'm just going to be twice, I'm going to be multiplying 2 to this expression for t. Okay. So Vx well, hold on. This is going to be Vi. Okay, so then that becomes all right. Vi cosine theta times 2 Vi sine theta over G. You may or may not recognize this trig identity, but okay, so we have Vi squared, 2 cosine theta sine theta over G. That just becomes Vi squared sine 2 theta over G. So this is a horizontal range equation in terms of theta. Very helpful because this equation here, it basically tells you that there's a double angle scenario that's going to achieve the same horizontal distance. And those double angles are all complements of each other, which means that if I project an object at 35 degrees, I will get the same, and I achieve a range, I'll get the same range at its complement, which is 55. You can put that in there and verify for yourself. Let's just assume that, let's do that. So if Vi is whatever it is, let's say that these are equal, so these are constant. They won't change. We know gravity doesn't change, and we project the cannonball at the same speed every time. So those are basically unity. That I can just take those out of the equation. And so I can say sine 2 35 something. And let's see that sine 2 55. They should be equal. You put that in your calculator. So do we get that? So it's roughly 0.939, 0.939. And you don't have to worry about these numbers. You just know that they're equal, that there is an equality between the complements for the horizontal range. And we see that picture on page 79, you know. So I just wanted to show that a little explicitly. So the maximum range is achieved 45 degrees because the double angle for this function, well, produces the largest number. So maximum range at 45 degrees. Sines and cosines, same value at 45 degrees, maximum range at 45 degrees, all that. So that's just the blurb on projectile motion. We'll come back for practice problems the next time. So any questions?
Why is the max range at 45 degrees? Sorry.
The max range of 45, you get the largest distance at 45 degrees just because the value is the largest at 45 degrees.
And that's just for the example you gave, or that's in all cases?
That is in all cases.
Okay.
Because we're just using this we're using this equation for maximum range or range, yeah. So you can, one last bit we can show about that. Another way we can prove that that is the case is to take a look at the sine and cosine functions. If we have, what is it? Pi over 2. And we know that cosine does this bad boy there, and then sine does this. It's 1 and all that stuff. Well, look at this intersection point. That's roughly pi over 4, 45 degrees. They share the same value graphically, mathematically, and it computes into maximum range in physics. Physics problem there. So just another way of helping you appreciate that this concept is the same, that you get maximum value at 45. And so there's another coterminal of 45, whatever that would be, 3 pi over 4, I'm not quite sure, but so all the places where they intersect, that's your 45 degrees, and they share the same value, and they have the maximum range. And because look here, so if this is like, if this would be say 35, you know, for cosine, well, you know, kind of doesn't fit because we're using only one sine component. So it's 35 for cosine, but sine of 35. They'll be well, they're off. They're not the same, right? Sine of 35 and cosine of 35 are not the same. But only 45 is the same for both sine and cosine. And all multiples of 45, all 2 pi multiples. So hopefully you get some more appreciation for that. Any final questions? Oh, okay, that's it for today. I'll see you tomorrow. Okay. All right.